Alright, so yeah, here's my notes. As usual, you can scan this QR code in the bottom left to follow along, because sometimes I rush through the notes a little bit too quickly. So if you need to backtrack and copy stuff down that I skipped over, that's on the left there. On the right, we have a mailing list and feedback form. This is the same one that we've been having in the last few weeks. So if you haven't joined that mailing list already, I do recommend it, because I'll email just updates to that list, and also like the recordings after the workshop. And yeah, if you want to give me feedback, you can do it through there, or you can do it through my experience, which is opened up now. I'm always looking to improve my workshops, so if you have any feedback on what I can do better, please, that would be very appreciated if you could leave that. Okay. Yep. So for today's lesson, we're going to talk about pile foundations. So, of course, this is in contrast to shallow foundations, which we've been doing for the last 2 weeks. So, in week 7, we've been doing bearing capacity of shallow foundations. In week 8, we've been doing settlement of shallow foundations. So, pile foundations or deep foundations, we can actually squeeze both the capacity and settlement into one lesson, because I'll be honest, this is the easiest week of content so far. So, you'll be chilling, at least for the stuff that which will be in the final exam. So yeah, of course I've started at 11, 14 or something, because yeah, just gauging based on my 9 a.m. class, we can fit everything in an hour and a half. It's pretty chill. All right, so we'll have 4 questions to go through, but first I'll go through the theory, and we'll do a quizzes right after that. Yeah, you got a question, Mike?
Sorry, we just got an email from the lecturer about an extra tube next week as well, and that's also covering files. So it's like a week application.
Wait, did you say an extra tube?
Yes, I think it's because we missed one with the history.
Yep.
I know you did the reported one.
Yep.
I'm wondering whether this is accurate ahead or
do you know what time the extra?
there's 2 options. It's in the afternoons online on Tuesday next week. And they reported as well.
So I haven't been emailed about that personally, or maybe I have and it went to spam, I don't know. But no, but I think I won't be taking that. I think Babak's probably going to be taking that on. And so I think his thinking is that so that the tutors don't have to do an extra lesson or whatever. Yeah, so I'm pretty sure Babak will be. I've just done an extra lesson because I don't mind doing it, but yeah. Anyway. Okay, let's talk about piles. So we're going to start very general as usual. We're going to talk about the difference between driven piles and board piles, okay? So this is basically how they're installed. And I know this seems really random, but it does play into the calcs a little bit. There is a factor which will depend on this kind of information which will be given in the question, right? So the idea is that driven piles is kind of so imagine you have a plank of wood, and you have a hammer and a nail. That's what a driven pile is. A driven pile is essentially the equivalent of the nail, and you bang it in. That's a driven pile. So it's also called a displacement pile. So it's called displacement pile because it displaces the soil as you bang it into the ground, right? And in contrast, there's something called a bore pile. And if we're continuing the wood analogy, you have this plank of wood, and you get your drill bit and your drill, and then you can screw it in, take out, so it creates a hole essentially, and then you cast concrete into that hole. That's what a board pile is. It also has a few other names, right? So it's also called a non-displacement pile, because it doesn't directly displace the soil laterally, how you would bang in a driven pile. It's also called a cast in situ pile. I think that's Latin or something, I don't know. Cast in situ means cast on site, and that's just about how you pour concrete into that hole on the site, right? Does that make sense? These will be all the terms you need to know regarding these 2 types of pile installations, right? Okay, the next thing you have to note is the difference between an end-bearing pile and a floating pile. So an end-bearing pile basically has a rigid layer at the bottom of the pile. So this could be any kind of rock, but it's just, again, we've mentioned this a couple of weeks in a row, but soil is a much weaker material than rock. So that the soil is essentially your soft strata, and rock is generally in these calculations is considered a rigid layer that wouldn't move or settle, right? Yeah. Whereas a floating pile is all within your soft strata, all within that that soil material, essentially, right? That's it. That's pretty much all the overall terminology that you need to learn. Here I have a little tree diagram of what goes into pile design, right? And the majority of our efforts we focused on single piles because you learn that groups of piles is actually just an extension of single pile design. There's not that much extra content in this tree. So we're mainly looking at branch 1 there, so single piles. And we'll be designing for ultimate capacity, just like we've been doing for shallow foundations, and we'll be designing for settlement as well. So here, this last little bit of the tree, I've just kind of divided it into based on the equations you'll be using. So for ultimate capacity design, it matters whether your soil is drained or undrained. You'll learn that, at least in this topic, it's actually a very simple difference. So drained and undrained is about how the soil behaves in the presence of water, right? In other words, how it flows through and all that stuff. But effectively in this topic, drained just corresponds to sands and gravels, and undrained just corresponds to clays. It's that simple, right? And floating and end-bearing piles, again, is what I covered just above, and that's just to do with how the pile, the bottom of the pile sits, right? Does that make sense so far? Okay. So here's the ultimate capacity equation, right? We call that PU, for a single pile. And this is a general formula, so we haven't started talking about whether this is specific to clay or whether this is specific to sand. This is just as general as it gets, right? And PS stands for our shaft capacity of a pile, and PB stands for our base capacity for a pile. So it actually helps to look at these two diagrams here, which I've drawn. So you can have a circular pile, you can have a square pile. At least in this workshop, these will be the only two cases that you see. However, these shapes can be hollow as well. I'll tell you how to deal with hollow shapes later, but it won't be in the workshop. But you might be able to expect a hollow cylinder kind of pile in your exam, or a hollow square shape, right? Okay, so we can break down shaft capacity and base capacity further, right? So these units will be in kilonewtons, essentially. And for our first component, which is our shaft component, that will be Fs, which is our shaft strength, multiplied by our shaft area, right? Similarly, FB is our base strength, multiplied by our base area, right? Trust me, it doesn't get much harder than this in this workshop. It's pretty chill, okay? So, the area of the shaft and the area of the base is literally from, what is this, year 8 geometry or something? So what we're doing to get the shaft area is the blue highlighted area. So this is kind of our shear area. If you remember from fluid mechanics or something. It doesn't really matter. It's just going to be our circumference, right? Our circumference of that circle multiplied upwards by a length, right? All we care about is that outer shell kind of area, okay? And then our base area for a circular pile is going to be the area of a circle, right? And here's the area of a circle in terms of D. So yeah, you've probably seen this one, pi r squared, but yeah, we'll just stick with diameter. This is the diameter version of the formula. Okay, and for a square pile, the area of the shaft is going to be the perimeter, right? Perimeter, S, S, S. That's 4 S's, right? So 4 S's multiplied upwards by the length. That's it for the area of the shaft, right? And then for our base area, that's S squared. Area of a square. Okay, so pretty sure, right? Okay, so let's talk about these components now, Fs and Fb. So this is the strength of the shaft and the strength of the base, right? these are dependent on the type of soil you're dealing with. So here I've called it the drain strength, but this is again analogous to pretty much just sand. And then there's a formula underneath here called the undrained strength, but that's again analogous to clay, right? This is the overall formula that you're going to be punching into your calcs, but here I'm just going to break down specifically Fs that plugs in. That's this component here, this Fs, right? So Fs is made out of two smaller components, right? One is the average effective vertical stress, right? So let's talk about that first. So in an effective stress distribution, so this is from soil mechanics, we essentially care about the average along that shaft, okay? So if your stress distribution looks like this, for example, just, yeah. Actually, to be honest, I'll screw up this shape. It'll never look like this. It'll look like this. Okay, so say your stress distribution looks something like this. It's going to be that area divided by the length, okay? So I'm someone who loves to avoid integration wherever possible. And so this is my cheetah formula. So you calculate the area of that shape separately and divide it by its length, okay? F, okay, we'll talk about F later. But, so your average will be whatever that average is, but at the very base of your stress distribution, that value corresponds to sigma VB dash, okay? So that's the effective vertical stress at the bottom. That's actually the easiest part to get, I guess. Like the average stress might be a little bit more complicated, but the bottom one is always just that value at the very bottom, the base, right? Okay, let's talk about F and NQ. So that's what I've highlighted in green and in yellow, right? So F is the shaft friction coefficient, right? It's equal to all this stuff, okay? But you don't really need to know what those things are. Like obviously, if you want to look at the notes more deeply, I've included what they are. But essentially, all you care about is the shaft friction coefficient, and that's this, right? And for NQ, this is the bearing capacity factor. So what these two, I guess like constants are, they're a function of what I was talking about earlier, whether a pile was driven in or bored, right? As well as a function of the soil consistency. So we care about whether our soil is loose, medium, or dense, right? Once you get that information from the question, you just pick whatever value corresponds to that, right? I guess this makes more sense as well as we see a question with it, but yeah, just keep in mind that's where that's from. For undrained strength, we actually don't care about the vertical stress distribution, right? It's actually a function of adhesion. So adhesion is the cohesion multiplied by something called alpha. Alpha is a reduction factor, right? So your cohesion is always going to be bigger or equal to your adhesion, essentially, right? How you find adhesion is literally, say you have 100 kPa of cohesion, which is given in your question. You go up to the line, you bounce off of it, and then whatever value you get there on the left, that's your reduction factor. You multiply the cohesion by that. And this graph is really nice to read because it's not logarithmic or anything, so each of these lines is just linear, right? Okay, I want to talk about one more thing, and this is RS. So RS is a slenderness reduction factor. So I'm going to draw something on the board quickly. Okay. So you have various classifications of piles in terms of its slenderness ratio, right? So slenderness ratio, I'm going to use that word a few times today, right? It's just a ratio of the length of the pile divided by d. So don't be confused. Lowercase d in the pile topic is referring to diameter, right? Sometimes it's uppercase d, by the way. But both these don't refer to the depth like we did for shallow foundations. it's referring to this diameter here, because L refers to this kind of vertical dimension. It's really stupid, but I know. So, as you can see here, we have a few kind of ratios that you can see. So this is called a slender pile. This would be, I'm just going to call it a stubby pile, because that's what they call it in for columns, for like concrete, right? And most of the time, we're going to have a slenderness ratio, which is somewhere in the middle between slender and stubby. So our slenderness reduction factor is only accounting for piles which essentially have the ratio of a straw. So imagine like a straw that you sip water with. It has to be super thin compared to its length, right, in order to have this reduction factor even matter, right? But I've included the formulas for that anyway. So RS, in the normal case where your slenderness ratio is less than 50, less than or equal to 50, it's just going to be 1. So that's all of this stuff over here, right? And then, yeah, it can get lower and lower if it's really slender, essentially. Does that make sense? Yeah. Okay. Next, we have something called FB. Oh, sorry. FB is just the base strength. And CUB is the cohesion to pile diameters under the bottom. Okay, so I'll just draw that out real quick. So say you have clay, because we're talking about clay here, in one layer, and then we have clay in a second layer, right? And so we have a pile that looks like this, right? If our pile sits like this, 2 pile diameters under, we might have a different cohesion value to the cohesion we've been using for that top layer, right? So what 2 pile diameters under means is in the niche case where 2 pile diameters is a different cohesion value to what the base of, like the cohesion at the base of the pile is, that's when you have to do something slightly different. But most of the time, it's just going to be your regular CU value that you've been using. So like, if it was like that, you just use the CU that you've been using for that. So NC is a bearing capacity factor that depends on the slenderness ratio. So why I've bothered to draw all of these cases out is this is kind of a stubbiness, it counts for the stubbiness case where like the slenderness ratio is really small, right? So if your slenderness ratio is really small, you have kind of like a stubby pile, right? Most of the time, you're gonna have something on this side where it's not super stubby, and in which case your bearing capacity factor is 9. But sometimes you have to reduce this bearing capacity factor if it's a really stubby case, right? And we'll actually see that in today's workshop. Okay. Does anyone have any questions about strength so far? Okay. Let's talk about settlement. So again, we're going to be talking about both the capacity and the settlement for deep foundations. Basically, the settlement depends on whether you have a floating pile or an end-bearing pile, firstly. But the formula for settlement for a floating pile, I thought this was pretty funny, right? Is that it's literally piles, right? So you can remember this really easily. It's P times I divided by LES. So the formula for the settlement of piles is literally piles, okay? Most of these are quite straightforward, but it's a function of the point load that you put through your pile, firstly. That's P. P is the point loading that runs through your pile. And then the length of the pile is L. ES is the modulus of the soil. This is all given stuff. What you have to calculate is the influence factor, all right? So the influence factor comes from this graph, right? This graph is a bit more annoying because it's logarithmic, okay? So you have to account for that. But it's a function of 2 things. In other words, in order to get your I, you need 2 things first. The first is your pile stiffness factor, which is equal to this. So it's a ratio of the modulus of the pile material, so that's usually reinforced concrete, divided by the modulus of the soil, right? Then you have to multiply it by something called RA. And RA is a ratio of area, okay? Which is the net section divided by the gross section. These words might be trigger words if you do steels as well, but the idea is that the gross section is the area which is encapsulated by the outer shell of the pile, hollow, okay? So it doesn't matter if it's hollow or not, that's always the gross section. The net section is just the section area, essentially, including if it has holes in it. In other words, including if it's hollow, right? So like a hollow circle, you'd have a different net and gross section area, right? The idea is that all of the piles we'll see in today's workshop won't be hollow, okay? So we'll have a ratio of area of just 1. So if it's solid, it's just gonna be 1, right? But if you do have a hollow pile, you just have to account for it by using this part of the formula, essentially, right? That's what I mean by this is totally reasonable to include in the exam, because yeah, it's not that much extra effort just to account for the hollow pile, right? Okay, so we talked about floating piles, right? Which again is just piles, and this will be, for example, sand, and we're talking about the settlement here. But you can have a few different cases. So that's a floating pile where it's just sitting on a, it's just sitting in the sand, and there's no like rigid rock layer or anything like that. End-bearing piles are the ones where you have a rock layer at the bottom, which is like a rigid layer that doesn't move. Then we have different formulas to account for that. But we also have a kind of like intermediate case where there is a rock layer, but the pile is still considered floating because it sits all within the sand layer, right? But we can just kind of adjust this case slightly. Okay. So what I'm going to talk about before I talk about end-bearing piles is floating piles with a rigid layer underneath, right? So this is actually best represented using this graph here. So H, similar to the settlement topic, is just going to represent the depth from the top of the soil to where the rock layer is, okay? That's what our correction factor is. The rest of this is the same formula, so you'll recognize S equals piles. That's the formula of settlement for floating piles. We just have to multiply it by this correction factor, okay? That's a function of the slenderness ratio as well as this like height to length ratio. Make sense? Yep. Okay. End-bearing piles are calculated slightly differently. The main thing is that this is called a movement ratio rather than a influence factor or something like that. But none of this should be super hard to calculate once you've learned the other normal case, right? Cool. Let's talk about pile groups lastly. So pile groups are kind of an extension of how you calculate the single pile. Like you have to learn how to do the single piles first, and then you can do pile groups too. So pile groups are dependent on whether you have a floating pile or end-bearing pile, right? So there's two failure mechanisms for floating piles, okay? It's the sum of the individual pile capacities, right? So say, for example, I'll just draw out an example, it'll be easier. So say you have 9, 10 is 9, 3 by 3. You have a 3 by 3 grid of piles, right? What you're going to do is you're going to calculate the pile capacity for a single one of these piles, assuming they're all like the same dimensions. And then you're going to multiply it by 9, if you have 9 piles. Right? The other thing you have to do is check for block failure. Okay, so block failure is something that's exclusive to floating piles. So, essentially you have to calculate the failure of a block that encapsulates this entire, 3 by 3 grid of piles. Right? And then you have to check the minimum of those two, and that's what your capacity for a floating pile group will be. Lastly, actually not lastly, I have to talk about settlement as well. But for end-bearing piles, it's simply the sum of the individual capacities. So for end-bearing piles, we don't consider the block failure case. Okay, lastly, for settlement, right? You have to get the settlement of an individual pile, right? And then multiply it by something called a group correction factor. A group correction factor depends on whether you have a floating or end-bearing pile, right? So the top table here, the top table here is referring to just floating pile groups, whereas the bottom table here is referring to end pile groups. And so you're going to get slightly different numbers, but essentially you have to calculate the same thing for all of these. That's your slenderness ratio. That's your stiffness factor. This one's kind of new. S refers to spacing, right? So spacing over diameter. You have to calculate that as well. So what spacing is essentially the spacing between these piles, center to center. That's what spacing is, right? Okay, does that all make sense, guys? Okay, what I'm gonna do is I'm gonna pull up the Quizziz, do the Quizziz, and we'll have a break. Once I pull up the Quizziz, I'm gonna turn the aircon because it's really hot in here now.
Makes sense. This doesn't make sense to me. One thing that looks and then do you have like oh, they're retaining no. I didn't. That's a compliment. I haven't done it. I'm taking leave for my like starting Tuesday.
All right, has everyone joined? I'm gonna start soon. Make sure to scan the QR code if you're joining.
Yeah, no, I'm not going back until like for like 3 weeks. I'm doing it not the soul, but I'm doing it. I don't do this one
All right, has everyone scanned and checked into this? I'll give you like 10 more seconds. All right, we're gonna get started, all right, guys? Good luck. seconds. All right, 10 seconds. Everyone's done. Okay, cool. Good job to these people. I love the names. Let me bring this up. Nice. So yeah, it's exam period. Steals is due soon. That's all I'll say. All right, so this is kind of a stupid question, sorry, but like basically it's just to get your head around the idea of the surface areas that we care about. So yeah, basically AS is the red part of the Coke can, and AB, we only care about the bottom area there, right? Yep. Okay. All right, so for this question, let's have a zoom in on it. Gonna mute that. All right, so yeah, we have this pile in loose sand, and we're given the material properties on the left here. So it's just trying to get your head around what each of these material properties denotes, right? And it's basically unit weight of soil. Whenever we see the unit weight, at least in this course, we only really care about the soil. Yeah, if you see it in concrete, it might be a different story, but yeah. Gamma there refers to the unit weight of the soil. So E refers to elastic modulus, of course, and ES specifically, we're talking about the soil material, right? EP refers to the pile material. Okay, so this kind of caught me off guard because in concrete, EC is the concrete material, but yeah, in this topic, EP refers to the pile material. Okay. Yeah, and if you do like solid, if you do steels right now, this might have done your head in a little bit because it's just some random terms you might have seen from steels. But it's really not that complicated. It's just yeah, soil and pile, right? Okay, so basically same question, but we have the stress distribution that I've drawn on the right. We care about two particular points. If this is a cohesionless soil, so again, we're dealing with sand here. So we care about the average stress acting on the shaft, and we care about the stress at the base, okay? So in order to get that, you have to multiply the unit weight, right? To get the stress, we multiply the unit weight by essentially the depth to these points, right? So because this is uniform, there's no effect of groundwater, the average stress will actually just be in the middle of the layer, right? For all of the stress acting on the shaft's like surface area. And to get the effective stress at the base, we multiply the unit weight by 6. So we get that. Okay, so here we have a rectangular pile. Well, I think it's a square pile actually, but same thing. The pile strength components we need, right? So essentially, we're going to deal with layered questions quite a bit, right? We care about the we care about the average vertical stress in the middle of the sand layer, not necessarily the middle, but for the sand layer, right? And the average vertical stress for the gravel layer. In this case, because there's no water effects, these will both be in the middle, okay, of these layers. And we always care about just the base of the entire pile. So we don't, some of you guys might have chosen the, PB sand. We don't care about the base at the interface between the materials. Like we don't care about the base strength there. We only ever care about the base strength at the very base of the pile, okay? Okay, so this one's probably one of the harder questions, but it's because the effective vertical stress we only really care about it for sands and gravels. Okay, we only care about the average vertical stress in the sand in this case, because the sand isn't the layer with the base either. Okay, so for clays, just remember that the strength of the clay layers is a function of adhesion, so it has nothing to do with the vertical effective stress. So we only care about it at depth equals 5 because that's the middle of the sand layer there. Okay, all right, yeah. Lastly, this is to do with pile group failures. And so for a floating pile, there's 2 ways it can fail. The first way is that you have to calculate the sum of the individual piles, right? So if there's 9, you multiply the individual capacity by 9, or the block failure. And yeah, that's just the entire block of soil that's encapsulated by that volume. And then you have to test that as well. So you actually have to test both of these for floating piles, floating pile groups. All right, cool. So I'll give you a break and we'll come back at 12.
I didn't want to respond to you, I saw your message. When I saw your message, I wanted to start and then tell you a story. And then like a day passed, I'm like, I'm just going to respond to you about the start. I messaged you, and I literally was like, I just had a start. Wait, good we're getting high. Yeah. Yeah. What the heck? I like don't even and then looking at when's the go? I'll be there as well. When do you get off? Like, so I'll be so they will look very nice with me. Okay, that's fine. That's cool. That's not a experience. Just think about I'll be doing this now. Which work is this? Why is that not very much? What is this? What is this? Oh, that was. I'm working on that. Oh, they need to know. Oh, really? Because I saw the machine for you. So basically, you update the cell back. And then update cell back. And this is how the tool is. Every time they put on, they that's so cool. Is there like that's nice. So you don't have to do any like oh really? That's actually really good because I never got that experience. Because mine was here's a retaining wall, go design it. And I was like, what the fuck? Dude, come on. I was like, oh, that's really? And then I started like, I'm doing it. Even to this day, they're just giving me like, I don't know. cheese tasks. Whereas like, serious analysis, I actually like that. And are you looking at such a thing? So then I'm in a meeting, I'm like, yeah, I'll do it. And I'll shake my head. And I sit down, I'm like, so then I end up like asking them all like my questions.
Similar to actually.
Yeah, it's very similar. It's just the calculation jobs I haven't given us. It's just January calculations. It's like I won't do that until I'm now. So maybe it's so easy.
Is it site based role?
Yeah, I've started to decide.
Oh,
I'm going to decide like
oh,
2 times. And just see processing those.
they're easiest calculations out of all the weeks.
Did you apply? Did you apply yet?
Oh yeah. You sure you want to take out your application? It's calm. Oh, you should both come.
She's like coming, otherwise why is she not coming?
Why should we do professional development?
It's only 2 days. I only come if she comes.
It's over a weekend as well.
You know, just because
fine.
like,
It'll work
that
with work.
period, it's very like, you know, it's so many weddings. You can skip one wedding.
Wait, is it a weekend that's already blocked out by
Almost a
the
weekend. Like these
You have-
weddings,
You have like 5 weekends.
Can you throw up just one day and then the day for
That's actually allowed, by the way. If you want to like drive, like organize your own transport, you can drive.
Friday and then you leave on Saturday, so you understand on Sunday. I know you have family stuff on
Is it
Saturday.
over?
You have family stuff on Sunday.
no, it's Saturdays. Oh, what's your phone?
They can't.
Has every weekend's been blocked out already because they haven't fully decided what day it'll be. It'll be one of the early like term 3 weekends.
I know she has family plans every Saturday.
And so, if I don't go, I'm dead.
You're dead.
I'll be dead.
Why?
I'll literally, I will ask you to make that again.
Oh my
I don't,
goodness.
they don't care, that's it.
Every Saturday.
It's good. It's charity because before the geology exam, I asked Hannah like, hey, study, and she's like, no, I'm hanging out with family.
Priorities.
And then the
Priorities.
day before, like, FaceTime, and I was like, oh my goodness.
Well, see if you can make it. Can't.
Yeah,
Not
I'm
in the world.
pretty sure.
But why wouldn't you just come anyway?
Because Anna's not coming. John, get it.
You should come to professional development.
If you sell it to John.
Yeah, it's hard to sell right now because the tickets aren't out yet. We don't have anything to show, but next term we'll have like some
It's a
stuff.
fun thing to have over the weekend.
And it's just like meet like 30 or 40 years outside of a tutorial setting. It'll be fun. It'll be good fun. Well, regardless, you guys should come to the revision study session.
I think I'll do that.
That'll be in week 11. So, you know, like no class in week 11, but just like throughout like the weekdays.
That's awesome. You see how you go, yeah, I'm coming. I'm like, I'm glad. And then you say you're not coming, and then I thought for 2 seconds, and then like, I don't want to go to the lecture. So I was like, I'm enjoying this.
You follow the Instagram. So I don't use Instagram as well.
I didn't use any.
Well, you can follow the Facebook.
Yeah, I
Follow
use
the link to Mark. No, that only does like the recap after the project. So Facebook okay. Well, if you guys only come on Fridays and Thursdays.
I see. You're the
so we do like the recap workshops and like the short sessions as well.
That's Fridays? Instead of Fridays?
Just come on in. More information content. That'd be good. It's just like this vibe, but oh, there'll be a crash course. Run by me.
Yeah, I need to go to that. I haven't watched a single lecture.
Oh, you're right. Yeah. It's okay.
I'm moving up. Like, I'm going to study on Tuesday. Like, I'm going to finish the assignment. And then I'm not going to study until my next. Then I'm going to
Alright guys, we're just gonna continue now. So, yeah, we'll go through the questions. Here's the first question. So this might be slightly familiar because like I included some of the theory and the diagrams from Quizziz on it. But what we have here is we have a pile in a sand layer, right? And the pile is 6 meters deep into the sand layer, and it has a diameter of 500 mil. We're also told that the pile is driven, right? And we're told that we are dealing with loose sand. So that will be important for when we're looking for the factors that we have to multiply everything by. Okay. So the first thing we have to do here is determine the allowable vertical capacity, and the second thing we have to do is determine the settlement. Okay. So the stress distribution is going to be just one straight line because we only have one layer with like a homogeneous material that we're assuming. So we're pretending that the entire thing has a unit weight of just 18 kilonewtons per meter cubed, right? So we talked a bit about how to calculate this, but essentially to find the average vertical stress along the shaft of this pile, all we have to do is just go halfway down, essentially, right? So that's equal to, what is it equal to? 54 kPa. And to get the vertical stress at the bottom, we just multiply it by 6 instead. So 18 times 6. That gives us, what does it give us? 108. Right? Makes sense? Okay. One just quick note here is that, yeah, if you remember in like 1300 and all those other courses you do statics, you do a free body diagram with all your point loads and uniformly distributed loads and stuff, and then you kind of put the shear force diagram immediately below it. What this does is it saves you from having to write the dimensions twice. So we're doing something kind of similar, but it's just for the stress distribution. So stress varies linearly downwards, right, with the depth. So we're going to overlay it kind of to the right. So that's what I like to do. So you can draw your pile right on the left, and then to its right, I would recommend, that's where you can draw your stress distribution, right? Okay, cool. So next we're going to calculate the geometric stuff. So that's the area of the shaft and the area of the base, right? So since we're dealing with a cylinder shape, the area of the shaft is going to be the circumference, right? So that's the circumference there. Right, it's basically the perimeter of the circle, multiplied by L, and L is going to be 6 meters. Let's keep everything in meters. Here I've written lowercase d, but lowercase d and uppercase d in this topic is just both going to refer to the diameter, so that's fine. But we should do everything in meters, so that's 0.5 meters, right? That gives us 9.425 meters squared. Cool. Okay, so the area of the base, even easier. It's going to be pi on 4 d squared. That's the area of a circle, right? Where d is 0.5, right? That's giving us 0.196 meters squared. Okay, cool. So we're going to do one more thing, and that's calculating our factors that we have to multiply to get the strength of sands, basically. So we have our F factor and we have our NQ factor. Okay, so these, let me highlight them to color code them. These are going to be a function of whether your pile is driven or bored, as well as the consistency of your soil. So that's soil density, right? So from the question, we were told that we have a driven pile and it's in loose sand. Okay. So what I'm going to do is I'm going to paste this table in. Sorry, I'm going to find a space for this table. Okay. So from this table, let's highlight it. We have loose sand, so that's going to be that top row. Okay, I've highlighted in purple. And then it's a driven pile, right? So that's those two columns. What we have to do is we just go across like this, and then we find our values. So it's 0.8 for F and 60 for NQ, right? Make sense? Yep. Okay. Next, I've just put in our formula for, I guess just like, this is a simple, this is the P of the shaft, and this is the P of the base, right? So this is in a simple case what our capacity for this pile would be if we only have one layer, right? So like that's just the layer of the sand, right? Let's plug in everything, okay? So we pre-baked up here the average vertical capacity, 54. Let's write our units so that we don't screw anything up. F, 0.8, okay. Area of the shaft, we've pre-baked 9.425 meters squared, okay. The stress at the bottom, 108 kPa. NQ, we said was 60. And the area of the base, 0.196 meters squared, okay? So that's where all our numbers come from. That gives us 1679.5 kilonewtons, okay? Yep, so that's our capacity of our pile. What we do is we plug that in for our allowable capacity, because remember, our allowable capacity is just our ultimate capacity divided by some sort of factor of safety. We were given that the factor of safety in the question was 3, okay? So that gives us 560 kilonewtons, and that's our final answer. That's our answer for the capacity component, okay? Now we're going to calculate the settlement. Does anyone have any questions? I apologize, I see some people scribing, but I'm going to have to scroll down. What you should do, does anyone need the QR code again for my notes? Nope, okay. Let's continue with settlement, okay. So, settlement is going to be this formula. This is the piles formula, right? Funny looking one. It's going to be a function of pile stiffness and the slenderness ratio, okay? So let's first calculate the pile stiffness. So this is based on material properties. We were told pile material was 20,000 MPa, told that the soil material was 40 MPa in terms of its stiffness, right? Yeah, just keep in mind, sometimes you're given everything in kPa, in terms of elastic modulus, but the units cancel out anyway when it's plugged into this formula, so you won't really have to worry about it, at least in this case. Okay, and then the ratio of area is going to be 1 because we're dealing with a solid pile. If it's solid there and doesn't have like a hole, our ratio will be 1. Okay. Our slenderness ratio is going to be 6 meters, which was our length of the pile. Right? And keep in mind, even if this pile runs through different layers, so we'll see questions where this is like sand, this might be gravel. This L that we're talking about isn't the layer of, isn't the length of the layer anymore. We're talking about the length of the entire pile, right? So for settlement, we're talking about L as the length of the entire pile. Okay. Okay, that's going to be over the diameter, which is 0.6. Make sure these are in the same units, right? So if you have 6 meters over 600 millimeters, you can get the wrong number, okay? Because this is unitless, essentially, right? Oh, sorry, I forgot to write the number for past terms. That was 500. Okay, so we're going to need to use these two on the graph in order to get our I factor. Our I is our influence factor. Okay, so if we look on this graph, we see these L on D, like the slenderness ratio of like 200, 100, 50, 25, and 10. So we don't see the one for 12, so we literally have to draw it. So that blue line, sorry, it's a bit hard to see, that L on D ratio is going to be 12, okay? Our pile stiffness is going to be 500. So this is a logarithmic graph. So you see 100 and you see 1000, but luckily this dashed line in between represents 500. So it represents 500 in between, which is the number that we have. It goes up, hits the line, bounces off, and that's where we get our influence factor, okay? Guess what this influence factor is? Your head. It's 1.6. It's never the one that you think it is. But it's okay, there's a tolerance in the final exam, so if you're off by a little bit, hopefully we'll be right, okay? So, that's I accounted for. I is unitless, so that's fine. But, while people, sorry, I'll scroll up if people are still copying that down. Does anyone still need this? Does anyone still need a photo of this or anything? Because I'm gonna rub it out again. Okay, I'm gonna rub it out. Alright. So we actually kind of have to use different dimensional. Yeah. Turn it off. Oh, sorry. Yeah. Alright, so basically you want to stick to the same kind of set of units that all work with each other, like and just convert between them. And so for settlement, we generally work with millimeters, and so we should convert everything to newtons and MPa as well, so that everything's satisfied. Yeah, capacity, aka part A, we use like kilonewtons, meters, kPa. Stick to these kind of sets of units. So what I mean by that is that we were told that we had a pile loading of 400 kilonewtons, so we should convert that to newtons again. Right? 400,000 newtons. For L, that's the length of the entire pile. We want this in millimeters, so instead of 6 meters, we want millimeters, okay? Soil modulus was actually given to us just in MPA, so that's fine. So if we keep all those consistent, we're going to get settlement in millimeters, which is good. That gives us 2.7 millimeters, and that's the answer. Okay, is everyone happy with that? Yeah? Okay, we're gonna have to move on. Sorry, I think we were like scribbling. Please, well, I'm just gonna put my QR code up again. Copy of my notes on the left. Please scan that if I'm rushing ahead too far, because yeah, I can't like. I'm trying to like pace the workshop so that people who don't write stuff down don't get bored, but people who are writing stuff down don't have enough time. So essentially, I need you to scan that if you do need my notes. We're gonna have to move on to question 2 here now, right? So the difference between question 1 and 2, there's 2 main differences. The first one is we have multiple different layers of different materials, but we're still dealing with like cohesionless materials, and so we'll be using more or less the same formulas. And this time we have a square pile, okay, rather than a circular one, so that'll change our calculations a little bit as well. So let's read through this. We're dealing with loose sand, and our pile is driven, right? So that'll help with our factors. And then we have then we also have a medium density gravel. So this is all to do with the factors regarding like soil consistency. No groundwater, and we need to determine the vertical capacity of the pile with a factor of safety of 3, okay? So what we're gonna do, I know I said you should overlay the stress distribution on the right here, but I wanted a bit more space to draw out the stress distribution, so I've just drawn it down here. Just have a think about what this shape will look like, right? So we have 15 kilonewtons per meter cubed on our top layer, and then we have a more dense material on the bottom, right? We basically have 2 straight lines like this, except we have a greater slope for the unit weight that's bigger, right? 15 compared to 20, okay? So we're gonna have to calculate these key points here, firstly, and we do that using the unit weight and the depth. So the unit weight was 15, we multiplied by 5, because it goes down by 5, 75 kPa. And then at the very bottom, we have to carry on the stress distribution is this way, so this amount is 75, right? Now we have to add on top this slope, which was 20, multiplied by a depth of 5, okay? This gives us 175 kPa, right? So now we have these kind of 2 critical points. In fact, one of these critical points is straight up gonna give us the vertical effective stress at the base. But now we have to figure out what the average vertical stress is for each portion of these parts of the pile shaft in each layer, right? Sorry, that's a mouthful, but it's basically just saying halfway in this case. So it's not going to be halfway if you have the effects of groundwater playing into it, which we'll see in another question. But yeah, so for now, we just care about this being halfway. So this goes down 2.5 meters. Sorry, that's a really bad 2.5. This goes down 2.5 meters as well. It's a 2, sorry. Oh my god, disaster. All right, anyway. So, to get the average vertical stress in the sand, we basically just average what the top and bottom points are. So the top is 0, because obviously it starts at 0. And then the bottom of that layer is going to be 75. So to get the average, we just half 75 essentially, right? That gives us 37.5 kPa. That's one of our values that we care about. The other value we care about is going to be the average of the gravel. Okay, And that's going to be, basically what we do is we take the average of these two numbers, right? So the average between 75 and 175 is going to give us 125. Right, so now we have all of the numbers that we care about, right, and we move on. So, like what was in the quiz, we have to find the shaft capacity of the sand, the shaft capacity of the gravel layer, and then just the base capacity of the gravel, because we only care about that very bottom part of the pile. So this will look like this, right? And this one is NQ, VB, AB. Okay, so let's refer to this table, okay? So, we were told that we're dealing with driven piles. So immediately we just have to focus on these two columns, right? Because the entire pile is obviously either going to be driven or bored, right? So, since we're dealing with driven piles, and we have two layers we care about. We have a loose sand layer and a medium gravel layer. We're gonna have to go across and find the values we care about. So the friction value for the loose sand at the shaft is gonna be 0.8, and the friction value for the gravel is gonna be 1, okay? So from the NQ side of the table, we only care about the NQ value at the base, right? Which sits in the gravel layer. So we only care about the value 100 and not 60, okay? Let's see how that plugs in. This top one will be 0.8, this one will be 1, NQ will be 100, yeah? Since we pre-baked the average stress here, this was above, we're gonna plug in, let me do it in purple, 37.5 kPa, right? We have 125 kPa for the shaft in gravel, and then lastly 175 kPa for the base. All right, so let's deal with the areas, right? So for the area of shaft in sand, we care about this essentially. And remember, it's a square. So essentially we have to do this. This is a square. And we need the perimeter of the square, right? And we multiply it by the length, right? So the perimeter is 4 lots of the side length, and we should do everything in meters here. So it's 4 lots of 0.6 meters multiplied by the length, which the length in sand was 5 meters, right? And the length in gravel also happens to be 5 meters. I'm just going to duplicate this. But obviously if the sand and gravel layers were different values, you want to plug in the L corresponding to the length of the layer of the shaft. Okay, and then lastly, area of the base is just referring to this square area. Right. So that's 0.6 meters multiplied by 0.6 meters. So not too bad. Cool. So when we plug everything in, we're going to get these values. We get 360 kilonewtons for the shaft in sand, 1,500 kilonewtons for the shaft in gravel, and 6,300 for the base, which sits in gravel. Right. So the ultimate strength, the ultimate capacity, which is a force, right, is basically just the sum of all of these. So we add these together, and we get 8,160 kilonewtons. We're not quite done with the question yet, because what we have to do is we were told to calculate the allowable capacity, right? So the allowable capacity is just dividing out PU by the factor of safety. We were told to have a factor of safety of 3. And that's our final answer here. I'll just highlight in purple. Yep. Cool. Does that make sense, everyone? Yeah? Sorry, everyone's still drawing and highlighting, so I apologize, but I'm gonna have to move forward. Okay, so again, this was on the Quizziz. This is a slightly more complicated scenario, but if you remember, we only really care about the average effective vertical stress for the sand layer. We don't really care about the clay layers, because the clay layers only really care about adhesion, right? So here I've drawn sigma dash v as a I've just drawn to the right basically of the of our arrangement. So here's how it works. You might not want to copy down what I'm about to write first, because I'm just going to tell you what the slopes look like first. Okay. So basically the slope here is just going to be gamma t of the first layer. So that's the brown clay layer, right? The slope here is going to be gamma t, and you're going to have to subtract the unit weight of water, because as I mentioned in previous weeks, when you submerge soil in water, you have kind of a lighter net unit weight because the buoyancy of water kind of lifts it up, right? Similarly, we have everything else subtracted by water, because all these layers are submerged now, right? These are the slope values we're going to be using, right? But I'm going to erase this because I don't have enough space on the right to keep drawing it. But we're going to have to calculate some points. So we'll do this point first. This is the clay material before it's been before it touches the water, right? So that's a unit weight of 16 multiplied by 2 meters. Is 32, right? Now when it touches the water, we add on the residual stress from before. So this amount was 32, right? So we add on that 32, and we add on 16 minus 9.8, 9.8 being the unit weight of water. We multiply that by another 2, because it goes down by another 2 before reaching the next layer. That gives us 44.4 kPa. Okay. I'm going to highlight that. Next, we care about this point here. Let's draw it over here. So we have that residual stress, and we add on, so the density of the second layer, the unit weight of the second layer is 21. And we have to subtract off the unit weight of water. So, right? And then we have to multiply that by 2 meters because it goes down by 2 meters, right? That gives us 66.8 kilopascals. Right, I'm going to highlight that as well. But essentially, the point we actually care about is the middle of this sand layer, because we care about what the average vertical stress is, effective vertical stress is acting on our dense sand, right? So the way we get this is averaging these two numbers. So if on your calculator, you can go 44.4 plus 66.8, the whole thing divided by 2. That gives us 55.6 kPa. So that's the number we're going to be using in the following calculations, okay? So again, this was just pre-baking something for the sand layer, but what I'm going to do is I'm going to do it in order of the layers going downwards. So I'm actually going to switch over to the clay layer first. So in this first clay layer, the formula for clay strength is this, clay capacity rather. So we're told that the clay layer has a cohesion of 30 kPa, right? Let's look at this graph first. So we're looking at this graph here. So if you if you read this graph as 20, 40, 60, 80, 30 would sit somewhere in the middle between these two, right? And it hits the top. But what alpha is alpha is a reduction value. So you can't ever really get an alpha above 1. So what happens is you just go across the side and you get that alpha is 1. Right? So sure, alpha is 1. This is now our adhesion component. It's just basically those two multiplied together. Alright, next we have to calculate the area of the shaft that is in this clay layer. So that's this here. And this is a cylinder, right? So circumference multiplied by length, right? This is 0.6. Remember, do everything in meters. The length is 4 meters, right? That gives us 226.2 kPa. That's the strength of our shaft in the brown clay. Okay. Good question. Does the color of the clay affect how strong it is? Not for the calculations at least. As in, they'll tell you the material. Yes, it's color, bro. Like, yeah, they just call it a different color to refer to different layers. Okay. So for dense sand here, right? And keep in mind the density of the sand does matter because that's going to affect our K value. Our formula goes like this, right? So again, I'll do it in blue. We've already calculated this. That's what we spent ages looking at that graph in the top right doing. F is going to come from this table, right? So remember in the question, actually I'll show you. Sorry, I didn't say this in the question earlier. But we have a cast in situ, right, pile, and we have dense sand, right? So when we look at our graph, we're looking at board piles, aka cast in situ, and we're looking at dense sand. So we also don't care about the NQ factor. That's the factor highlighted in yellow because our sand layer is not the base, right? So we only care about the shaft factor, which is F. I'll highlight that as 0.7, right? That's 0.7 there. Area of the shaft is pi dl. Let's replace those values. 0.6 m, and we have 2 layers in sand. 2 meters in sand. So replacing that with 2. That gives me that PS2 is 146.725. Cool. Moving on to our grey clay layer. So again, this is to do with alpha and Cu and As, right? So we're still talking about the shaft component, but this is at the bottom clay layer. Cu for this one was much larger. So instead of 30, it was 120. Okay, we go to the graph. 120 sits over here, right? Bounces off, right? What do you reckon that number is, guys? 0.45, sure. Okay, so AS, same as above essentially. Pi times 0.6 times 2, right? That gives us 203.575 kilonewtons. Yep. That gives us all of the shaft components, but of course we still have the base. Here's the first time we're seeing an example clay being used as the base of the foundation. So this formula looks like this. Okay, so let's talk about CUB first. So CUB is the cohesion 2 pile diameters below the base. If you look at our question, there's not like there's no like rainbow clay or something underneath there, so it doesn't really matter. We're just going to take the grey clay's cohesion value. So that's going to be 120. Okay, for the area of the shaft, that's just a circle. and that'll be in meters squared. Okay, so let's talk about NC. So, as you saw on the right, these slenderness ratio calculations mostly are concerned with like clay, right? So clay will care a lot about the slenderness ratio. So let's calculate that first. Alright, so let's look at this pile, right? What do you think L is for the base of this pile? Like, we were calculating, yeah, anyway. We don't take L as 2, right? So, I'm sorry. We care about the base, so it's not based on the shaft, it's based on the entire like pile, right? So L is going to be 8. This is a slenderness ratio for the entire pile, right? So it's the entire pile that's subject to buckling, essentially, right? And so our pile diameter in meters is 0.6. Keep in mind that should be in meters. That gives us 13.3, right? That's greater than 4. So we know we don't have the case of a, this is the stubby case, right? So yeah, we don't have like a super stubby pile. In which case, our NC factor is our normal number, which is 9, right? Makes sense? So we sub in 9 for this, giving us the PB is 305.36 kilonewtons, okay? So, lastly, PU is going to be the sum of all these. Two 226.2, 146.7, what is that? 25? 203.575 and 305.36. Okay, cool. We're going to add all that up. That gives us 881.86 kilonewtons, okay? So, one thing about this question that's just slightly different, it's not a big deal, is we don't actually need to calculate the allowable capacity because that's not what the question asks for. So when it says what load would cause failure immediately, right? That's actually referring to PU, right? We don't have to calculate any kind of like allowable load. Yeah, and we don't get a factor of safety anyway in this question. So we're just calculating for PU. So I'm going to leave it as PU, but yeah, just keep that in mind. Any questions so far? Okay, cool. We're going to move on to our last question. So our last question is a pile group, but there's nothing funny happening with the layers this time. We just have clay, and if you remember, for clay, we don't need to do a vertical stress distribution. That's only a sand-related or sand or gravel-related kind of feature, right? So let's read this. So we have 9 piles in a 3x3 grid, right? Each of these piles have 600 mil diameter, and they run 6 meters deep into the ground. Yes. Yeah, and then I've just written a couple of other things off to the side. So like just material properties that we'll need in our calculations as well. So the first step we have to do is determine the capacity of the pile group. It says assuming no interaction between the piles. So what this means is the sum of all the piles' individual capacities. That means 9 times whatever capacity we have for a single pile, right? In step B, we're going to calculate the block failure. So that's assuming there is interaction between all of the piles. So that's the soil block, that like the volume that encapsulates all those piles. And then C, we have a factor of safety of 2, and we're going to calculate the minimum basically between A and B, and then apply a factor of safety. And then for D, we have to calculate the settlement for the entire pile group as well. So this is kind of like an exam style question in that there's multiple parts, but they all logically like flow on from each other, right? So let's do it. So for clay, our pile shaft strength was this formula, the adhesion multiplied by the area of the shaft, okay? So we were told that CU is 100, and using the graph, we can go up and left. What do you reckon that is, guys? Actually it's 0.52. So it's 0.52, guys. Yeah. Alright, so yeah, that's 0.52, right? Okay, so the area of the shaft is going to be pi multiplied by 0.6. So remember, that's the circumference, multiplied by 6, which is the length of the pile that goes up. That gives us 588.1 kilonewtons, okay? Sure, that's the pile strength. So of course, pile strength is a lot easier to calculate when we don't have multiple layers, right? When we just have one layer, this stuff ain't too bad. Okay, let's do NC, CUB, AB for the base component. Again, the cohesion, 2 diameters under the base is going to be just CU, so same thing. It's going to be 100. And the area of the base is going to be the area of a circle, d squared being 0.6 squared. Right? Okay, let's talk about NC. So NC, again, depends on the slenderness ratio. So we have 6 over 0.6 here, right? Because the length of the entire pile is 6, diameter is 0.6. That gives us 10. 10 is greater than 4. That's all good. So NC is 9. Again, that's the normal case. I'm going to chuck in 9 here. All right, cool. So capacity of our pile is 588, which is our shaft capacity, plus 254.5, which is our base capacity, giving us 842.6 kilonewtons, right? Okay, sure. So one more thing we have to do to calculate the strength of the pile group when we sum them is just take that number and multiply it by the number of piles, which in this case is 9. So the number of piles. Right? That gives us 7583.46 kilonewtons. Okay, sure. That's the answer to part 1. So again, these formulas aren't bad when you only have one layer, right? Cool. Next, we're gonna do block failure. So I'm gonna rub this part of the board out. So if we have a 3x3 grid of piles like this, do you think it would make more sense to do it center to center, as in get the block of soil between center and center, or encapsulating and including the radius of all of these circles? So to be conservative, we take the greater volume, which is all of that, including that radius, right? So what this ends up being, so this is the radius of your pile. There's also radius. This value here is your spacing. So the term spacing is only in this topic for pile groups. It's how far they're specified, of course. So this whole side length here is going to be 2 lots of your spacing plus your diameter of your pile, right? Because the diameter is 2 times the radius, right? Sorry if it's a bit dark here. Yeah. So that's what we're gonna do to get the side length, and then, yeah, we'll see how that plays into everything. One more thing you have to consider for block failure is that, and this is my first time learning about it too, I just saw it in the solutions. When you're dealing with block failure, you just take alpha as 1, right? You assume that the adhesion and the cohesion is the same thing. Don't ask me why, but you do. So if you remember from before, let's look at that alpha graph. We would have taken alpha as 0.2, right, based on the soil cohesion value. But we're going to replace that instead of 0.52 as 1 and still have this really high cohesion value. And then our area of our shaft we're going to be calculating is going to be this. Right, so we have to get the perimeter of this block and multiply it by that length. Okay. So perimeter is 4 lots of, basically this here, when you add them all up, is 6.6 meters. So that's the side length, right? So 4 lots of 6.6 meters times 4 meters, 6 meters, sorry. 6 meters is the length of the pile, right? So that's your shear area. Sorry, shear area, shaft area. Yeah. It's actually both, but anyway, yeah. Okay, so that gives us 15,840 kilonewtons, right? So next we have to calculate the base for this soil block. If you remember, that's this. So if we consider this whole pile group as a block, right? Do you remember, I had it up on the board before, but do you remember like the case of the stubby pile? It kind of behaves like that now, okay? Because the slenderness ratio is going to be really not slender, whatever number that is. Low. Yeah, it's going to be really low, right? So it's going to be, the length is going to stay as 6, so that's the length into the ground, over our diameter, which is now our side length, right? That's 6 over 6.6, giving us 0.909, okay? 909 is a lot lower than our threshold, which was, I believe it was 4, right? So what we have to do, so before our normal case is that we have NC is equal to 9. If you look at this formula here, it can get as low as 5.6, but we're going to increase it as like an interpolation kind of thing by our slenderness ratio. So we're going to plug in for our slenderness ratio 0.909. Okay, that will give us 6.373. Okay, so instead of 9, we're getting 6.373 for NC. Yeah. CEB is going to stay the same, so that's 100. And the area of the base is just going to be 2 times, the side length times the side length. Right? That whole thing will give us 27759.6 in kilonewtons. Okay? Cool. And to get our ultimate, we basically just have to combine the shaft and the base strength, giving us 15,840 plus 27759.6. This is 43,600 kilonewtons. So that's our value if we consider the block of soil encapsulating all of the piles, right? One small note I've made here is also that you can apparently calculate this as a shallow foundation using like Hanson's equation and all that stuff, but I wouldn't, because this is a lot easier to do it the pile way rather than the shallow foundation way. And I think the reason for this is because when the slenderness ratio is low enough, a pile is almost considered like a shallow foundation. Yeah, because remember, shallow foundation looked like this, right? So it's like, it's B value, the depth into the ground, all that stuff is, yeah, it's quite stubby basically compared to a pile. Does anyone have any questions? We've got 2 more parts, so part C and part D, and then we're done. Part C is basically saying, all right, so because we have a floating pile group, there's 2 failure mechanisms, right? You have the sum of the individual piles, right, and that's that capacity, and you also have the block failure capacity, right? So we have to take the minimum of those two because it's whichever one's going to fail first, right? The numbers were these. So 7,500 roughly for the first part, and 46,000 roughly for the second part. So of course the first part's way weaker. So that will be our PU, right? Our capacity for our group of piles. And then PA is our allowable capacity. So we just have to divide through the factor of safety. In this case, our factor of safety was 2. So we have 3,791 kilonewtons. So that is PA, and that's the answer for part C, right? Okay, lastly, we're going to do settlement, right? And specifically, we're going to do settlement for this group of piles, right? So the first thing you have to do is determine the settlement for an individual pile. And if you remember, for an individual pile, right, looks something like this. You simply have a point load, right, which is your P. Maybe not that. It would have been something around the ballpark of 400 kilonewtons, right? So that's going to be a function. Our settlement will be a function of this value, right? But we have a point load of 3,600, which is really high, being applied to this entire pile group, right? So what that will look like is the point load will act on the pile cap, which is like a concrete kind of slab, which connects all of the piles in this pile group, right? And so if you look at it top down, your force is going to be applied maybe at the middle, and you just have to assume that the force is distributed evenly between all of the piles, right? So what I'm trying to say, essentially, is you have to divide this number by 9. So you take P, which is a really large number, and you divide it by 9 because we have 9 piles, okay? That's 400 kilonewtons, okay? Sure. So that's the number we're going to roll with for when we're calculating the settlement of a single pile, right? So we do our piles formula here. So that's the formula we use for if we have floating piles, remember? Okay. And remember, we should keep everything dimensionally consistent for settlement. So let's start plugging in our numbers. So instead of 400 kilonewtons, we should do 400,000 newtons, right? Multiplied by whatever the influence factor is over the length of our pile was 6,000 millimeters, and our modulus was 20 MPa. Okay? Cool. Let's figure out our influence factor. And the influence factor is a function of stiffness. Let's see if I can do these colors consistently. Our stiffness and our slenderness ratio, right? So, basically our stiffness, the values were, we had 2,000 MPa for our pile material, and we had 20 MPa for our soil material, okay? And we're dealing with a solid shaped pile, right? So our RA is going to be 1. Stiffness gives us 100. Our slenderness ratio is going to be 6 on 0.6, right? 0.6, yeah, diameter of just a single pile again, remember? Gives us 10, okay? So, wait a minute, these weren't the highlighted colors that I used earlier. Okay, whatever, sure. So, we refer to this graph here, and that's going to give us our influence factor, right? So what we have to do is we have to locate the curvy line that represents our slenderness, right? And so our slenderness ratio was 10. Luckily it's drawn on here, thumbs are right. And our pile stiffness is 100. What's the influence factor, guys? This one actually makes sense there. It's 1.9. But that's only because the lines were already drawn on there, so there's no error really. Anyway, so we plug in 1.9 to that equation, and we get our settlement in millimeters, right? So So sure, the settlement of one of our individual piles is 6.3 mil. Okay. And now we have to determine something called SG. So our SG is basically our settlement of the entire pile group, but we have to determine RG. RG is the kind of like multiplication factor to account for like the interaction of the piles with each other and how much they settle by. Luckily, we've already calculated K, L on D, but we haven't calculated SD yet. So K was 100, slenderness was 10. S on D is spacing, so 3 meters on a pile diameter of 0.6 meters, right? Giving us 5, right? So now we have to refer to the table in order to get RG. So that's these two tables here, but it's not that bad, right? So basically, we have to first choose which table we're gonna do, right? So here we have floating piles, right? So that's the piles that aren't sitting on like rock or anything. So we're doing we're just gonna deal with the top table. So our slenderness ratio, right, was 10. Our spacing ratio was 5. We had 9 piles in our pile group, and we had a pile stiffness of 100. Okay, so what this kind of looks like, it's like this. So you're selecting these kind of rows. You filter it down even further into this row, this column. Filter it down, right? And we go across until we find our value we actually care about. Okay, so this value will be a different value if we're dealing with end bearing piles. So if I accidentally chose the wrong table, you would have instead gotten 1.12 or something, right? Sure. So 2.49 is the value we actually care about because we chose the right table. So RG is 2.49. Okay, so settlement was 6.3 mil, and we're going to multiply that by that factor, 2.49, and this will give our group of piles settlement. That is 15.77. Okay, cool. That's the end of the question. Does anyone have any questions? Yeah.
The first column only has.
Scroll down.
Yeah, it has like 10, 25, or 100.
Oh yeah.
Do you really extrapolate?
Yeah. So if they don't, okay, obviously, like it's an interpolation thing, right? But there's no way in an exam they don't give you these ratios as like an exact number. Yeah, because if you have to interpolate between these, it would be, I don't even think it's linear, like the interpolation. It would be like curved or whatever. So there's no way that they'd get you to linearly interpolate this. You can expect to find ratios and stiffnesses which are on this table. Yep. Okay, that's the end of the class. I'll see you next week for lateral, earth pressure, and retaining walls, I think. But yeah, that'll be our last class.